Okay, so are you ready?
Yeah, I'm fine, thanks.
Okay, so our second speaker today is Thomas Krämer from HU Berlin. So he's going to talk about bit Tanaka groups on abelian varieties. So please.
Yeah, thank you very much for the invitation. It's a pleasure to speak at this seminar series. So I want to talk today about work in progress, which is joined with Ariane Jarampeka, Christian Lehn, and Marco Maculan. And this is an application of D-modules in arithmetic geometry. So I will talk about the geometric part, but I want to briefly give you the context before I really start. So the motivation is the following. If you have a number field, so a finite extension of Q, and you take finite set of primes, then Falting's theorem says that if you fix a dimension G, then there are only, up to isomorphism, only finitely many abelian varieties of this dimension G over that given field, which have good reduction outside S. So here I've drawn an elliptic curve with good reduction outside 17. But of course, the result is really interesting in higher dimension, but this one I cannot draw. Okay, so this is classical, but now more recently, Lawrence and Sevin have shown a similar result. I mean, in the general context of the Shafarevich conjecture, not for abelian varieties, but for subvarieties in a fixed abelian variety. So you take an abelian variety A, say of dimension at least 4. Then what they show is that up to translation, there are only finitely many smooth, ample hypersurfaces, Z inside A, all defined over this number field, which have a given fundamental class, say in the Néron-Severi group, and good reduction outside S. So they can be written with equations, with integer coefficients, which when you reduce modulo a prime outside S, you still get something smooth. So this is a general instance of the Shafarevich conjecture, which says that under certain assumptions, if you fix the numerical data for a class of objects, then there should be finitely many up to isomorphism, which have good reduction outside a given set of primes. And a key input in their proof, apart from methods from Pierre-de-Koch theory, is a geometric statement about the monodromy for families of hypersurfaces in abelian varieties, and this you can actually read over the complex numbers if you like. So this is really a geometric statement. And today I want to discuss only this big monodromy part of the result, but for higher codimension subvarieties. So the idea is, in general, we would like to extend this theorem to higher codimension subvarieties with certain positivity properties, and this is kind of the first thing one should try to generalize. So before I start, I just want to say what this big monodromy theorem says. So the setting is the following. You fix an abelian variety A, and you vary hypersurface or more generally a subvariety. So you take a constant abelian scheme over some base variety S, and inside it you have a varying family of subvarieties. And then you look at the monodromy of this thing. So you look at the cohomology, say in middle degree, Hn of the fiber. And then you have a monodromy representation. Once you fix a base point in the parameter variety S, you get a representation of the fundamental group on this fiber as a variation of hot structure. And what Lawrence and Sevin want for their proof is that for suitable families, Z, the Zariski closure of this representation will be big, meaning that essentially its derived group contains the full special linear group, or in situations where you have certain dualities, it contains at least the orthogonal or symplectic group. So it's as big as possible, a classical group acting by the standard representation, if you like. So the classical way of seeing this would be look at Hodge theory, if you want to express this variation of the family in terms of properties of a special fiber, if you take a S sufficiently general, and you look at this fiber, then this VS is a Hodge structure, and you can look at its Mumford-Tate group, and then the result by André, which is essentially the theorem of the fixed part, says that the Zariski closure here, if you take the connected component, then it's a normal subgroup of the derived Mumford-Tate group. So the two are very closely related, and if you show that the Mumford-Tate group is big, then the monodromy is either trivial or it's also very big. The problem is in their result, I mean, they don't apply this to the full family of all subvarieties with given numerical data, but only to smaller subfamilies, and it's not clear how to control either the Mumford-Tate group for those subfamilies or the monodromy. So in fact, they will have to do with subfamilies where the monodromy is not big in this sense. And then their insight was that, in fact, you are not forced for their proof to take here the cohomology with values in Q. You can replace Q by any local system on the abelian variety and restrict it to ZS. Again, you will get a nice local system, and you can look at the monodromy representation for this local system. And for their proof, it's enough to show that the Zariski closure of that monodromy is big. And it turns out when you vary this local system L, when you choose it generically, in fact, you can choose it to be a suitable torsion local system, then the monodromy can be shown to be big. But then you're no longer in the realm of Hodge theory, but you need a different tool here. And instead of Mumford-Tate groups, they use certain Tanaka groups, which are attached to D modules on the abelian variety. So this is what I want to talk about today. Today I will talk about the right-hand side. But the relation between the two sides is very similar to Andre's theorem. So when you can show the right-hand side is big, then you have shown the left-hand side is also big. The point is the right-hand side does no longer depend on L. So some of the right-hand side here computes the monodromy for a generic choice of L. So that's maybe the point here. Okay, so that's the general context. So in this talk, I want to give a general overview over these Tanaka groups. So first, I want to explain a bit of background about D modules. That's important later on. So this is very basic because I was told this is a very mixed audience, so maybe it's good to have some general background. Then I want to explain how to define these Tanaka groups and review their basic properties. And then in the end, I want to briefly say how you can actually show that these groups are big and how you can do this in any codimension. Okay, so let me first recall the notion of D modules. So the simplest case as a warm-up is D module on the affine line. So you take just spec C of T, and then differential operator on the affine line is just a polynomial in T and another variable delta, where this delta is the derivative with respect to T. And those operators form a non-commutative algebra. So this usually denoted C in brackets T, and then this angle brackets delta to indicate that delta and T do not commute. They satisfy this relation partial T minus T partial is 1, which is just an incarnation of the Leibniz rule. First multiply by T and then take derivatives is not the same as first taking derivatives and then multiplying by T. So this is a non-commutative algebra, but it's very mildly non-commutative. So differential operators you can filter by the order. So the filter piece Fn of dx is those differential operators which only contain the powers partial k up to, so partial 1 up to partial n. And if you take the graded for this filtration, then this non-commutative relation is deleted. So the graded is really a commutative ring, a polynomial ring in two variables. because this psi t minus t psi, this is the symbol of this commutator, which is a symbol of 1, but considered in the degree 1, so it becomes 0. But of course, you should view this more intrinsically. If you look at how differential operators transform under coordinate changes, you see that intrinsically this ring is the ring of functions on the cotangent bundle. So before we proceed, I want to show you just 2 toy examples. So the structure sheaf is a D module. So when I say D module, I always mean left D module here, just by taking derivatives. And you can write it as a quotient of the free D module dx modulo the left idea generated by partial. And now you can dualize this definition and get a skyscraper D module by modding out the left idea generated by T. This is now as a sheaf on the affine line, it's concentrated at the origin. So it's a skyscraper sheaf, but it's not coherent as an OX module. It's only coherent as a DX module. So the OX coherent skyscraper sheaf OX modulo T, there's no way of making this into a D module. Okay, and again, you can, taking the order filtration on D, you get nice filtrations on these modules, and the graded pieces are modules over this polynomial ring, those which you see here. So now if you look at the support of these objects, so the support of the modules downstairs on the affine line, in one case it's a full affine line, in the second case it's just a point. But if you look at the support of the graded objects, so this is supposed to be a cartoon of the cotangent bundle, then you see in both cases it's a line. In the first case, it's the 0 section of the cotangent bundle. In the second case, it's the fiber over the origin. And so this you can do more generally for any coherent D module. You can pick a good filtration, as in these 2 examples, and then you take the graded object and you look at its support, and this is called the characteristic cycle of this D module. And the filtration itself is not God-given. There may be different filtrations which are good, but one can show that the support is independent of the chosen good filtration. So of course you can now do the same in higher dimension. So say we are in the affine plane with 2 coordinates T1 and T2, then dx is just this non-commutative algebra with 2 commuting variables and 2 derivatives. And say you look at the T1 axis, Z here, then you can define a simple D module supported on that axis by just taking the quotient of dx by the left ideal generated by partial 1 and T2. So this is kind of mixing the first 2 examples. So it's the Dirac module in the T2 direction and the structure sheaf in the T1 direction. Again, this inherits a good filtration from dx, and if you take the graded objects, you see that the characteristic cycle is the vanishing locus of psi1 and T2, which geometrically is the total space of the conormal bundle to this T1 axis. And this total space of the conormal bundle to Z I denote by lambda Z. So here's a cartoon, and of course, once you know it in this case, you can do it locally for any smooth curve in the plane, for instance. You can define similarly a D module supported on that curve, and its characteristic cycle is precisely this conormal bundle to the curve. I mean, you just mod out the local equation and the tangent vector field. And this you can do also for singular varieties, and then it becomes more interesting because then the D modules you get will correspond to the perverse intersection complexes which compute invariance of the singularities of the subvarieties. But this is not what I want to talk about today. Today I want to talk about smooth subvarieties. So the D modules we are talking about here are even simpler, just these type of Dirac modules. But nevertheless, we will see singular D modules later on. And so we need this definition of conormal varieties also for singular subvarieties. And this is just the obvious definition. If you have a smooth ambient variety X and you have a singular subvariety in there, then the conormal variety to Z is just defined by taking the smooth locus and taking the conormal bundle to the smooth locus and then closing up. So that's the picture. In particular, this is again an irreducible variety, and over an open dense subset, it's just a fiber bundle. Okay, so now in general, the setup we work with is the following. So a smooth ambient variety. This will be an abelian variety later. And then you look at differential operators on that variety. And then for any coherent D module, M on the variety, you get a cycle, which by taking a good filtration and taking the graded and taking its support. The filtration is not unique, but the support is well defined. And this gives you a cycle on T star X. If you take a closed subvariety, you can always define a Dirac module, or if you prefer to think topologically, it's a perverse intersection complex supported on that subvariety. And its characteristic cycle in the smooth case is just the conormal bundle to the variety. In the singular case, it's still a sum of conormal varieties, but you may have some further contributions sitting over the singular locus. So what happens is you take a nice stratification of the singular locus of Z, and then some conormals to some of the strata will appear here as well. And which ones appear and the multiplicities you get have to do with local Milnor numbers of the singularities. Okay, in these examples, I've shown you the characteristic cycle was always a sum of conormal varieties. And this has a special name. So the D module is called holonomic if its characteristic cycle is a sum of conormals, which conceptually means it's a cone. This is always true, but it's a Lagrangian cone. So this is the smallest dimension which characteristic cycles can have. And the holonomic D modules, those form a nice abelian category, which under the Riemann-Hilbert corresponds to perverse sheaves. So all its objects are finite length. And we have a full 6-functor formalism on the derived categories. You can take push forward, pull back, external tensor product, and so on. And so we start with these very simple objects supported on smooth subvarieties, and then we apply all these functors to get very complicated objects. And of course, they are the principal ingredient inside those mixed Hodge modules. So we should really use them in algebraic geometry. And for Hodge modules, you have various other ingredients. You have filtrations and you have various conditions to have a Hodge module, but all of this will not matter today. Today, it's enough to just know what a D module is. We don't need any finer structure. So the goal is to use these functorial properties to say something geometric. Okay, so this brings me to the main part of the talk. So let's look at this Tanaka group. So now we specialize to the case where the ambient variety is an abelian variety, say over the complex numbers. Then when you have two holonomic D modules, you can get on A, you get a holonomic D module on A times A by just taking the box product. So you pull back via the two projections and then take the tensor product, the category of D modules. And then this you can push forward under the sum map because A is a group variety. And then you get again a D module on A, and this is called the convolution of the two things, M star M. So this is abstract nonsense. This you can do whenever you have a 6-functor formalism. I'm cheating a little bit, so properly speaking, I should work here in the derived categories, but all the geometry happens in cohomology degree 0. So to repair this, you have to divide out a certain subcategory, but I don't want to talk about this here. So this is only cheating a little bit. This is related to generic vanishing theory. This product, just by abstract nonsense, is associative and commutative and so on. So it gives you the structure of a tensor category on this thing. So I'm not using the usual tensor product, but this convolution product. And yeah, before I proceed, let's look at a toy example. So this is a stupid example. You just look at Dirac modules in points. So the skyscraper sheaf, delta A we had before. The definition of the convolution is made using the addition on A. So delta A star delta B is just delta A plus B. And thus, if you take any additive subgroup of A, then you can look at all those Dirac modules which are supported at points in this subgroup. And this will be a tensor subcategory of all holonomic D modules. And of course, giving a skyscraper module supported in a finite number of points just amounts to giving the points, and in each of the points saying how many copies of the Dirac module in that point you want to have. So this amounts to giving a finite dimensional X-graded vector space. And of course, graded vector spaces are representations of multiplicative groups. So intrinsically, if X is the group inside A, then X-graded vector spaces are representations of the Cartier dual, so of Hom of X into Gm. So any character of the group X gives you a representation of H. Okay, so here you see that this toy subcategory is just a representation category, and this now happens in general for arbitrary D modules. But there it's much more complicated to compute this convolution product. So you always have an equivalence of tensor categories, well, let me call it omega, from this category of holonomic D modules to the category of algebraic representations of some affine group scheme G, which only depends on A. And this group scheme is huge. So it's not an algebraic group, but it's a limit of algebraic groups. It's pro-algebraic. This is a bit like absolute Galois groups in number theory. So those are limits of Galois groups of finite extension fields. And here, this huge group scheme is a limit of honest algebraic groups corresponding to finitely generated subcategories in here. So the upshot is that here on the left-hand side, we have the convolution product, which is complicated but contains a lot of geometric information. And on the right-hand side, you just have the ordinary tensor representations of algebraic groups, which is very easy to compute. And so you can go both ways. And once you know the right-hand side, you can say a lot about the geometry on the left and vice versa. So this group scheme is too big for us to deal with, but it has lots and lots of interesting quotients. So for instance, for any subvariety Z in A, you can look at this intersection complex delta Z, so this Dirac module supported on Z. So this lives in this category, and then you send it to the right-hand side, you get a representation of this group scheme. Let me call this VZ. And now you can look at the image of this huge group inside GL of this vector space VZ. So the image of the pro-algebraic group inside this finite dimensional representation, this is now a closed algebraic subgroup of this GL of VZ, so it's an honest algebraic group, which is naturally attached to the subvariety. And the same you can do not just for subvarieties, but for arbitrary holonomic D modules, in fact. And these are the groups which enter in this big monodromy result by Lawrence and Stebbins. So these are the groups which we want to show are big when Z has certain positivity properties. So just coming back to these examples from the beginning. So if you just take a point, then the group for that point is the Cartier dual of the subgroup of A generated by that point. But there are more interesting examples already for curves. If you take a smooth projective curve inside its Jacobian, then this group can be computed, and it's a classical group. If the curve is hyperelliptic, then its image under the Abel-Jacobi map to the Jacobian is essentially symmetric under the -1 involution. And so this gives you a duality on the representation, and in this case, this gives you an alternating form, so the group is a symplectic group. But if the curve is not hyperelliptic, there's no reason for having a symmetry, and in that case, you get the full special linear group. So these are classical groups, and in some sense, the goal of this talk is to explain why this is a typical example. But I want to show you at least one example that it's not always that simple. So there are abelian fivefolds and smooth surfaces in there such that this group here is an exceptional group of type E6. So in some sense, this is still the biggest possible group given the symmetries of these surfaces, but it's not a classical group, so there's more way for examples here. Okay, are there any questions so far?
So do we know the dimension of the representation? So given
Yes, that's a good question. That's the next, I guess, on the next slide. So this is a topological information about Euler characteristics. So, so the first observation is these groups are reductive because these D modules are simple, so that the representations are irreducible. But we also know the dimension. The dimension is the topological Euler characteristic of the subvariety. In the smooth case, in the singular case, it's the same except that you have to replace the Euler characteristic by the intersection cohomology Euler characteristic. But otherwise it's the same. And for a general D module, what you do is you take the corresponding perverse sheaf and you take the Euler characteristic of its cohomology. So the dimensions are known. This is really topological information. In particular, you can say now immediately these three dots I had before, which you divide out. So when is this representation trivial? So it's non-trivial if and only if the dimension is bigger than 0, meaning that the topological Euler characteristic is non-zero. And for abelian varieties and subvarieties in there, having positive Euler characteristic is the same as being of general type. So this is why I put this sign here.
Excuse me.
Sorry?
Excuse me. Can I see
Yes.
the definition of G delta Z again? Can I see the definition one more? G delta Z.
Which one?
The group G delta Z.
Ah, yes, sure.
Definition again. Okay.
This one?
Image. I see. Okay.
Yes,
Okay.
it's the image.
Okay. Thank you.
Yeah, so this you should think of a huge group. It's a limit of groups, and this huge groups acts on some finite dimensional representation, and of course then it cannot act faithfully, but it acts via some algebraic quotient group, and this is precisely the image of this thing. So this image is an honest algebraic group, and it captures precisely the information which is seen by this representation. So you can view it differently. You take this representation and you take all its tensor powers and all their duals and summons and subquotients, and this will give you a tensor subcategory of this huge tensor category. And this tensor subcategory is the representation category of this this group. Sorry, this G of delta Z. So from a theoretical viewpoint, this is a very simple conceptual definition, but to actually compute this is a different matter. This is not so easy. Because you would have to control the convolution powers of this D module. which is usually hard. And today I want to explain a way around computing those things explicitly. Yes, so this is the representation. So it's non-trivial if and only if the subvariety is of general type, which is the same as saying, in this case, it's not fibered by abelian subvarieties. So you look at the stabilizer, which is defined to be the subgroup of points such that if you translate the subvariety by the point, then you get, again, the same subvariety. And if this stabilizer, this is always an algebraic subgroup of A, and if it's finite, then Z is of general type and vice versa. So those subvarieties which come from proper abelian quotient varieties by pullback, those we don't see, but all the others we do see. That's the moral of the story. And before I proceed, I want to make one further reduction. So usually, if you have subvarieties of abelian varieties, you can always translate them. And in many cases, the geometrically meaningful definition only gives you something up to a translation. For instance, if you have a polarization on a abelian variety, if you translate the divisor, the polarization class won't change. So it would be better to have an invariant which is invariant under translating the subvariety. The group G of delta Z itself will change, but it changes only mildly. So when you look at the connected component, G delta Z0, and then you take its derived group, so the commutator subgroup in there, then this will actually be independent of the chosen translator. So this is maybe the more meaningful invariant of the subvariety. Now, of course, this is only a subgroup in the original group. So you could wonder, if you start with an irreducible representation, don't I lose a lot of information when I restrict to this subgroup? But you don't lose so much. So the group of connected components is very easy to describe, and you can deduce that the restriction of this representation to this derived group is still irreducible if and only if the stabilizer is in fact trivial. So Z is not fixed under any translation. So just to compare with what we had before we had said that the representation is non-trivial if and only if the stabilizer is finite. Now, for having this irreducibility, we want the stabilizer to be trivial. But you see, once you have a finite stabilizer, then you can always get this first condition by passing to direct images under an isogeny. So up to isogeny, this condition comes for free. So now we are left with a connected semi-simple group. So this is like passing from a GLN to SLN. And the representation theory of connected semi-simple groups is very easy. It's governed by highest weights for a maximal torus. And what I want to explain here is that this representation theory geometrically gives you information about conormal varieties and vice versa. So for this, I have to say a bit more about conormal geometry. So one thing that's special about abelian varieties is because they are group varieties, the cotangent bundle is trivial, because you can just take translations to trivialize it. So T star A is A times V for some vector space V, which is the Lie algebra of A. Or I guess I should have put a dual here, sorry. It doesn't really matter. Okay, and so in this situation, you can define the Gauss map of subvariety Z as follows. You take the conormal variety to the subvariety. This sits inside this trivial vector bundle, and then you just project to the fiber V. So here's a cartoon. So what this means is, in the case of divisors, I mean, the conormal directions over any point are just a line. And you take a point on that line and you send it to that point inside the fixed ambient vector space V. So this is really like the definition of the Gauss map in real differential geometry, except that it's not on affine space, but on abelian variety. But the only thing you need to define it is this projection map from the cotangent bundle to the cotangent space at the origin. So this captures information about the curvature properties of the subvariety. And these Gauss maps see all the non-trivial representations, because we have seen already the representation is non-trivial if and only if Z has finite stabilizer. But this happens if and only if the Gauss map is dominant, which is the same as saying that it's generically finite, because here the source and target have the same dimension. And this is also why it's good to work with conormal varieties. I mean, the dimension of the conormal variety is always G, the dimension of the abelian variety, regardless of the dimension of Z. So this is a more symmetric picture. And again, in the smooth case, the dimension of the representation is the Euler characteristic, as we have seen, but this is also the degree of this Gauss map. So this is a very geometric interpretation. And in general, if you have a conormal variety, I define the degree of the conormal variety to be the degree of its Gauss map. And because we discard all those varieties whose Gauss map is not dominant, I say that a conic Lagrangian cycle on the cotangent bundle is clean if all components of its support have dominant Gauss maps, so if all of them have positive Gauss degree. So now we have a notion of characteristic cycles of D modules, and we have seen that the Gauss degrees of those cycles capture information about the D module. Now we want to understand the convolution of D modules in terms of characteristic cycles. So for this, we need a convolution product on cycles on the cotangent band. For this, of course, we use the sum map from A times A to A. And then if you have a morphism, you get a correspondence on cotangent bundles by first taking pullback under this morphism. And this other arrow is the co-differential of the sum map. So here everything is very explicit, because T star A is just A times V. The pullback is A squared times V, and T star of A times A is A squared times V squared. And the co-differential row here is just given by the diagonal embedding on the cotangent space. So V goes to V comma V. And this sum map var pi is just given by the sum map on the points on the variety. So A1 comma A2 goes to A1 plus A2. So this is a very explicit correspondence. And then, of course, when you have a cycle on T star B, you can take the push forward to a cycle on T star A by taking first the rho pullback and then the pi push forward. So this is how you define the convolution product on clean cycles. If you have lambda 1 and lambda 2 on T star A, you take lambda 1 times lambda 2. This is a cycle on T star A times A. And then you pull back and push forward. And you need to be a bit careful here, because I want to deal only with clean cycles. So anything which has non-dominant Gauss map is discarded. And so what I really want to do is you take a small enough Zariski open subset of the cotangent space, and you do this construction over that subset. You see which cycle you get, and then you take Zariski closure component-wise, keeping the multiplicities. So this way, it's by definition again a clean cycle. So you have discarded anything which is which has a non-dominant Gauss map. And then there is a classical formula by Kashiwara for the characteristic cycles of direct images of D modules. And in this framework, this says that if you have two holonomic D modules, then the convolution of their characteristic cycles in this sense gives you precisely the clean part of the characteristic cycle of M star N. So this is a very simple geometric definition which works for the clean part. If you want to do the same without the clean part, it would be much more complicated, because then in this push forward, you would have to deal with excess intersections and really work with intersection theory. But the point is that if you only care about those parts which are clean, then you can compute this naively. So I want to give you again, a toy example, namely a hyperelliptic curve inside its Jacobian. And say The curve has genus 2, so it's the smallest non-trivial example. And since it's hyperelliptic, you can embed it in a symmetric way. So if you have a point P on the curve, then minus P is also on the curve. And now we look at the summorphism from C times C to A. This is what we want when we want to compute the convolution product of delta C with itself. The image, because the genus of C is 2, the image is all of A. So this is a generically finite cover of degree 2. Then it's branched, of course, on the image of the diagonal, because A is birational to the symmetric product of the curve. So the branch locus is 2C. But it collapses fiber over the origin because of the symmetry. When you have a point P on C, also minus P is on C. So the anti-diagonal is collapsed. And if you look at this more carefully, you will see that the characteristic cycle of the direct image, the constant d modulon C times C, which is this convolution, this characteristic cycle is twice the zero section plus the co-normal to the branch locus plus twice the co-normal to this point where the fiber is collapsed. And this is the way you should think of this convolution product in general. So the characteristic cycle of a convolution gives you information about the fibers of the summap. Here it's very easy to do this directly, but I want to show this how to read this off from the definition I've given you before for the convolution of cycles. So first you need to compute the pullback of lambda c times lambda c under the codifferential. And this has three components. The zero section you always have in there. Then you have the diagonal component, all points P, P, V. V is a cotangent vector and P is a point on the curve. And you also have the anti-diagonal. Those are the points P minus PV. And now we have to look at the summap, var pi, which goes from this fiber product to T star A and sends PQV to P plus Q, comma V. And so by definition of the clean push forward, this zero section will disappear because the Gauss map is non-dominant. You have a zero here always. But the other two components you will see. And the situation is as follows. On the diagonal map, on the diagonal component, the summap is birational. It's essentially the map sending a point P to twice the point P. Whereas on the anti-diagonal, the summap is of degree 2. And here again, you see why it's good to work on the cotangent bundle and not just on the abelian variety. So on the abelian variety, this fiber here is collapsed to a point. But if you look at this on the cotangent bundles, you still get a generically finite map. The degree is 2 because you have the involution given by -1 on these points. Okay, putting together these degrees, we see that the pi lower star of the zero section is 0 and pi lower star of the diagonal is lambda 2c, and for the anti-diagonal you get twice lambda 0. And this gives you the clean convolution of the two conormal varieties. And as I promised, this is essentially the same as the characteristic cycle of the convolution, except that you lose this non-clean component, which is the zero section and has non-dominant Gaussian. And now the observation is that these multiplicities, which you see here, have a representation theoretic meaning. So this 1 here and the 2 here. And I want to explain that these can be computed without doing any geometry, just knowing the Tanaka groups. So in this case, it's not hard to see that the representation is just C2, and it's the standard representation of the Tanaka group, which is the full SL2 of C. In the standard representation, if you look at the maximal torus of diagonal matrices in SL2, you see that the standard representation has weights ±1. So if you look at the tensor square of this representation, then you have two wire group orbits of weights. You have the weights ±2. And this is an orbit which enters once. and you have the orbit of the trivial weight, which enters twice. So this V, tensor V, decomposes into a symmetric and an exterior square. And this weight 0 enters once in the symmetric square and once in the alternating square. So this is why you have a multiplicity 2 here. And now you can compare with what we had before geometrically. We have seen that the general fiber of the Gauss map for C, in this case, has 2 points, plus minus P or V. And this plus minus here is the weight plus minus 1 upstairs. And if you look at a general fiber of this new cycle, lambda C, call it lambda C, this has 3 points, the points plus minus 2p, which come from the diagonal when I push forward, and the point 0 v, which comes from the anti-diagonal. And because of the degrees of the maps, before the degree was 1 for the diagonal and degree was 2 for the anti-diagonal. So you find back these weight multiplicities as multiplicities in the characteristic cycle. So here, of course, the geometry is as simple as the representation theory. But the point is, if you take more complicated, I mean, if you take higher dimensional subvarieties, then the geometry very quickly becomes complicated. If you take a divisor on a billion fivefold, for instance, this is much more complicated. But once you know the Tanaka data, your group and the representation, then the combinatorics of weights is still very easy to deal with. And so this correspondence, which I showed you in this toy example, holds in general. So if you have a holonomic D module and you have this Tanaka group G, then you fix a very general cotangent vector V, and you look at the Gauss map for this characteristic cycle of M. And so you look at all points A, V, which are on the characteristic cycle. So this is the fiber of the Gauss map over that point, V. And then you project to the abelian variety. So you take all points A, which live in this fiber of the Gauss map for a very general V. So this is then a finitely generated subgroup of the abelian variety. And so we can look at its group ring. And it turns out this group ring receives a natural homomorphism from the Grothendieck ring of representations of G. And to make this work in practice, you rather want to work with connected semi-simple groups. And so here you should take at least the connected component. And as I said before, then maybe you have to pass to from M to its push forward under an isogeny on the abelian variety. And doing an isogeny means that here in gamma, you mod out a finite subgroup maybe. But this only affects the torsion part of gamma. So you still get a homomorphism to the quotient of gamma modulo its torsion subgroup. And on the left-hand side here, if you have a connected reductive group, then the representation ring is just the character ring. So X is the group of characters, and then you take the Y group invariance. So the upshot is more or less you get a correspondence between Y group orbits of weights for this connected reductive group on the left and irreducible components of characteristic cycles on the right, and this preserves multiplicities. So this is a dictionary which allows you to pass from representation theory to geometry once you know the Tanaka data. And the way to apply this is usually first you start with a simple enough D module M, where you can control the characteristic cycle. Then you can use this to get information about the Tanaka data. And once you have computed the Tanaka group like this, you have complete control, not just over this simple D module, but also over all its convolution powers. So first you go from right to left to compute the Tanaka group. And then once you know the group, you have a lot of geometric information. Okay, are there any questions so far? So this was just the abstract machinery. Now I want to come to the new part, how you can actually use this to show that these groups are usually as big as possible, which is very different from the behavior from our Tate groups, which jump widely in families. So the first reason why these groups are big is now easy to state. If you have a smooth subvariety, then this representation is a so-called minuscule representation, which means that its weights for a maximal torus form a single orbit under the Y group. The proof is now very simple. If the subvariety is smooth, its characteristic cycle is irreducible, and I mean the Y group orbits corresponds to the components of the characteristic cycle. So here there's just one component, so there's just one orbit of weights. So this is the setup for the smooth subvarieties, and in fact, I started considering these groups to understand singular subvarieties. But today I'm talking about smooth subvarieties for this Lorentz 7 application. So for singular subvarieties, these representations will no longer be minuscule, and you have a lot more freedom for the groups and the representations you get. But the punchline is, for smooth subvarieties, these groups tend to be as big as possible. And as big as possible, I'm saying, because minuscule representations of the simple Lie algebras are well known, and this is a very small list of them, so they are very special, and essentially they are only the standard representations of the classical Lie algebras, plus a few extra cases which you then have to treat by hand. There's one caveat here, because this is for the simple Lie algebras, but when you take two simple Lie algebras and you take their product, then a product of two minuscules of the two factors will again be a minuscule representation in this sense. So this finite list can only be applied if we know that the Lie algebra of this Tanaka group is simple, and this is the main point today. How can you see that this Lie algebra is actually simple? So a priori, I mean, this would only say that the Lie algebra is a product of simple Lie algebras, and the representation is a corresponding product of minuscule representations, which still leaves a lot of space. And we want to show the group is actually simple. And this, of course, doesn't hold for arbitrary Z, but then you have to impose some extra assumptions. And before I come to the assumptions, I want to show you a non-example, a trivial non-example again. Namely, if you take a product of two subvarieties. So if A itself is a product, A1 times A2, and if you take Z1 inside A1 and Z2 inside A2, and define Z to be the product of the two subvarieties, then you have the Kunnert formula for direct images, which trivially shows that the whole situation of the convolution product splits into the two factors, and so the Tanaka groups, GZ is essentially the product of the two groups. Maybe a modulo some finite central contribution, which doesn't matter here. So the Lie algebra of GZ is certainly the product of the two Lie algebras. But such examples are degenerate. And similarly, I should say, you can also take such a product situation and then divide out a finite subgroup, so pass to an isogeny abelian variety, then Z will no longer be a product on the nose, but only the isogeny to a product. But still, the Lie algebras will split as a product of two Lie algebras. And one way to rule out such examples is to assume that the subvariety is non-degenerate in the sense of Rand. So this is the following definition: a subvariety of an abelian variety is called non-degenerate if for any surjective homomorphism of abelian varieties from A to some abelian quotient variety B, if you restrict it to the subvariety Z, then the induced map from Z to B is surjective onto B, or it's generically finite over its image. So in other words, if the quotient map is not surjective onto B, when viewed as a map on Z, then it's necessarily generically finite over its image. And of course, this is not the case for product situations, also not the case for products up to isogeny. So this is one condition which rules out those cases. But you should note that this notion depends on the ambient abelian variety, which is not maybe not so surprising. I mean, we want to say something about the Tanaka groups, and they will also depend on the ambient abelian variety. But here the dependence is maybe even stronger. If you take something non-degenerate in A, and then you replace A by A times some other abelian variety, then it will become degenerate. So non-degeneracy is a very, yeah, kind of, you take, I mean, A should be generated by Z in the first place to have this condition. Okay, but let's assume this non-degeneracy condition. Then what we show is the following. So if you have a smooth subvariety and you assume its stabilizer is trivial, I mean, I said before, up to isogeny, you can always reach this, and this is just done to get rid of the connected components of the Tanaka group. Then the Lie algebra is simple in many cases you will encounter in practice. And for a more technical statement, so we don't have an if and only if condition, but we have many cases where we can say something. So I want to give you only two cases where we can say something. The first is if Z is non-degenerate inside A, and the restriction map from pic 0A to pic 0Z is an isogeny. So this two have the same dimension. This holds, for instance, when you have a complete intersection of ample divisors, and the complete intersection has dimension bigger than 1, so it's not a curve, because in dimension at least 2, you have a Lefschetz theorem for restriction on Picard groups, and so this is, gives you this isogeny condition. And of course, in dimension 1, this condition will fail. If you have a given abelian variety, you can find inside it curves of arbitrary high genus. So then pic 0Z will become arbitrarily large, and the dimension of pic 0A is fixed. So for curves, this doesn't work, but in higher dimension, this works very well, for instance, for complete intersections, which is in some sense the natural next case to try, where you could try to extend the Lorentz 7 result for finiteness of good reduction subvarieties. And the second case, so now we cannot say anything about curves. This is kind of embarrassing. So we have at least one condition which is fine for curves. So if Z is non-degenerate, not just inside A, but inside its Albanese variety, and if the dimension of Z is less than half the dimension of A. So as soon as A has dimension at least 3, this condition is certainly fine for curves. And non-degeneracy inside the Albanese is also trivially verified for curves. So the second condition covers all curves in abelian varieties of dimension at least 3. So for all those cases, we know that the Lie algebra of this Tanaka group is simple. And hence, being simple with a minuscule representation, we almost know that it's a classical group acting by the standard representation, except that there are finitely many exceptional cases to be dealt with by hand, and there are wedge powers of SLN, which also are minuscule representations, and those one has to also rule out by some different argument. Okay, so that's the main result, and the idea of the proof is to again use the correspondence between characteristic cycles and weights, which I discussed before. So the general effect is the following. If you have a subvariety Z with trivial stabilizer, and if you assume the Lie algebra is not simple, well, if the Lie algebra is not simple, you can look at the adjoint representation of the group on its Lie algebra. And then the Lie algebra being not simple means that the adjoint representation is reducible. It has at least 2 direct summons. And if you unravel this correspondence, you see that you will find effective conic Lagrangian cycles, lambda 1 and lambda 2, on T star A, such that both of them have degree strictly bigger than 1, so they are not conormals to a single point. And the characteristic cycle of this D module delta Z decomposes as a convolution of 2 cycles, lambda 1 and lambda 2. Up to isogeny, so to deal again with this connected component problems, you have to replace Z by its image under multiplication by some natural number. Now, this is a kind of strange condition, but it's a very strong condition. And the question is, how do you actually use this? And this is what we did. We used these positivity assumptions on Z to deduce that such a decomposition cannot exist under the given assumptions. So I'm almost out of time, so maybe this is a good place to stop. So if you want, I can say something about the proof later. So the proof is really conormal geometry. You start with a given conormal variety to nz in this case, which is smooth. And the point is really the conormal variety to this nz is irreducible variety. So on the left-hand side, you have an irreducible conic Lagrangian cycle, and you know that it's a convolution product of two other cycles. And this is a strong condition which you can rule out in those cases. So I think I can skip the proof and just say thank you very much for the invitation.
Okay, thank you very much for the talk. So are there any questions?
Could you say a word about how do the Tanaka groups related to the Mumford tables, apart from the fact that both arising from the Tanaka formalism?
Yes, this is a very good question, which brings me to the very first slides, I guess. To this slides maybe. Yes. So what happens here is, I mean, the Mumford-Tate groups you can also view as Tanaka groups, as you say, by just looking at the tensor category of Hodge structures and taking the subcategory generated by the tensor powers of this Hodge structure. If you just do it like this, and you don't take this twist by a local system here, there is no obvious relation between the two groups. Because to have a relation between the two groups, you would like to upgrade the fiber functor on this category. So the category has a fiber functor to vector spaces. If you go from representations of the Tanaka group, you can go to vector spaces. And this fiber functor is essentially taking cohomology of the twist by a generic rank 1 local system. So for this untwisted cohomology, there is no obvious relation with the Mumford-Tate group. But if you do this twist, so you take cohomology with values in a local system, then actually passing from a D module to the cohomology of the D module tensor this local system, this is the fiber functor on the Tanaka category of D modules. When you choose L generic enough, of course, when you take a generic local system L, you no longer have a Hodge structure on here. I mean, you would like to twist with a unitary local system maybe to have a Hodge module. But what you can do is you can, and this is what actually Lorentz 7 also do, you shouldn't twist by a completely generic local system, but you can twist by a torsion local system. And if you twist by a torsion local system and you don't just take this single local system, but take its full Galois orbits of conjugate torsion points, if you take the direct sum of all those things, you will end up effectively with the cohomology not of Z, but of a finite étale cover of Z. So what I'm saying is that cohomology with a torsion local system as coefficients is direct sum in the cohomology of some finite cover of Z. And when you look at this finite cover of Z, and if you look at its cohomology, then upstairs you again have cohomology with Q coefficients. So this has a natural Hodge structure. And so you can talk about the Mumford-Tate group upstairs. And these Tanaka groups should be, I mean, they are related to the Mumford-Tate groups. So not of the ZS, but of these finite étale covers of ZS. So I would conjecture that if you look at this whole tower, so the situation is special because we are inside an abelian variety. So you have these isogenies multiplication by integers. And so you have a whole tower of isogenies on A, multiplication by higher and higher integers. And so you can take the pullback of Z under all these isogenies. So you get a tower of abelian covers of Z, so to speak. So finite étale covers with abelian Galois group. And in this tower, the Mumford-Tate groups should stabilize in a suitable sense. And the Mumford-Tate group you get for these finite covers should ultimately, stabilize to the Tanaka group of these summons. This is more or less the image I would have. But for this, you really need to pass to this tower of covers. Yeah, I guess that's forced here. I mean, if you replace this intersection complex by a Hodge module, this is also something you could do. Then again, you have the problem that to get a fiber functor, you take the cohomology not of the Hodge module, but you take the twist by a generic local system. But if you are lucky and if you take a Hodge module whose cohomology already sits in degree 0, then actually the fiber functor is enriched in Hodge structures. And then the Mumford-Tate group of this cohomology will sit inside the Tanaka group. So in that case, the Mumford-Tate group is really directly related to the fiber functor.
Okay, thank you. And any other questions? So I'm kind of curious that suppose that we start with principally polarized appearance variety and take Z to be theta divisor, or
yes, this is what made me interested in these groups. So actually, I was quite surprised when I realized in this Lawrence 7 paper that it's interesting to have these Tanaka groups big, because I was coming to these groups because I was interested in singularities of theta divisors, for instance. And there it's usually, when you have bad singularities, the groups should become smaller, and that's the interesting case somehow. So both cases are interesting, but for different reasons. So if you have theta divisors, you can completely compute the group. When the theta divisor is smooth, then it's kind of boring. You get a symplectic group of rank G factorial. So the G factorial comes from the Euler characteristic, and symplectic because you can choose the theta divisor to be symmetric. So you have this involution, which gives you a bilinear pairing. So there it's clear what you get, but you can also look at singular theta divisors, and there it's much more interesting. So I tried a couple of low-dimensional examples. So for instance, in genus 4, these groups, when you vary them in the moduli spaces of polarized abelian varieties, they cut out the Jacobian locus, yes, and these theta null divisor. So they are closely related to the to this Andreotti-Meyer stratification by the dimension of the singular locus. So in fact, I think one can show that they refine this Andreotti-Meyer stratification. So there are two different layers in some sense. The first layer would be if you have a theta divisor, you take its conormal variety and take its Gauss degree. So just the conormal variety to the divisor and take its Gauss degree. And this gives you a stratification of the moduli space, and that one refines the Andreotti-Meyer stratification. This is an actual theorem, so it's, this you can show. But you can also ask about these Tanaka groups, and there it's a bit different, because as I said before, if you have very singular subvarieties, then the characteristic cycle will have more than one component. So in the characteristic cycle, you will have the co-normal to the theta divisor, but possibly also further components supported over the singular locus. And those also come into play. So a priori it's a different invariant than just the Gauss degree of the theta divisor. But still, it seems that this Tanaka data refines all of the previous stratifications, I should say. So the dimension you compute is not just the Gauss degree, but it also contains contributions from the singular locus. But if you have knowledge not just of the representation, but not just of the dimension, but of the actual group and its representation, then it gives you finer information. For instance, I think I don't remember precisely, but I think there are cases where the Gauss degree does not separate all the components of all the Andreotti-Meyer components. So it gives you kind of a weak solution the Schottky problem, but not a strong one in the sense that you have different components which have the same Gauss degree. And in that case, the groups are still different on the components.
Okay.
So the model should be the Gauss degree of the divisor is maybe the next invariant to consider after the dimension of the singular locus. But then if you want to go even finer, I think these Tanaka groups give you finer information than just their dimension.
Okay, yeah, thank you.
Yeah, welcome. And I should say maybe this group E6, which I mentioned, by the way, this also appears for a theta divisor. So this is for intermediate Jacobians of cubic threefolds. So there are interesting groups which are not classical groups and which do appear for theta divisors. But I mean, this is the only example I know for the moment, but just because it's hard to compute these things. I mean, I would expect similar things to happen in higher dimensions.
Mm-hmm. Okay, so any other questions? Okay, so yeah, since it's quite late here, so anyway, thank you very much for your talk. Yeah.
Yeah, thanks
Thank
for
you
the
again.
invitation.
Okay, so let's call it a day here. So we will meet again in 2 weeks. Yeah.
Okay, great. So I guess I can already say have a nice weekend, right? What's your